Hello, Luke. Welcome to Lesson 21. Today we're going to be talking about the product rule for exponents. And then we'll be looking at some addition of like terms with exponents as well. So, should be a pretty easy lesson today, I think. But let's see how it goes here. So, to begin with, let's just review exponents. So, we recall that if I have something like 3 squared, or 3 to the second power, this is essentially saying 3 times 3. That would be another way to write it, right? So we have the base, which is the 3, and then we have the exponent, which is the 2, right? So we're just taking the base, multiplying it by itself the same number of times as we have in the exponent, as the number in the exponent. Okay, so again, this is just review, but like 4 to the third is going to be 4 times 4 times 4. X to the third, if we have a variable, that's equivalent to x times x times x. Y to the third, again, is just the variable y times y times y, and so on, right? So those are all exponents. Pretty straightforward. So today, what we want to talk about is what happens if we have two constants or variables, and we are raising them to a power, and then we're multiplying them by something else. So let's say we have a 2 to the third power, and we want to multiply that by maybe a 2 to the second power. Okay, so we're multiplying exponents here, or terms with exponents. Okay, so if we're doing that, what happens here? Well, this one, because these are constants, these are numbers, we can actually figure it out. 2 to the third, that would just be equivalent to a 2 times a 2 times a 2, correct? And then we've got this other 2 here, so we have this multiplication sign we'll bring down. We have this other 2 to the second power. So that's just going to be a 2 times a 2, right? And now we could just multiply this whole thing out and get 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 again would be 32, right? So that's pretty easy. It's pretty straightforward. But let's take a look at this a little bit closer and see what really happened here, all right? So we took a 2, and we raised it to the third power, then we multiplied it by another 2 and raised it to a second. That gave us 3 2's being multiplied by each other, and then multiply that by 2 2's, right? So we could say that this expression, or this term right here, could be rewritten as 2 to the fifth power, right? Because we have a 2 being multiplied by itself, in this case, 5 times, 2 to the fifth power. So that would mean, if I just rewrite that up here, 2 to the third times 2 to the second, we could say that's equivalent to 2 to the fifth power. And if we look at this, what connections can we make? We can see that the base doesn't change. We have these 2 that are 2's, and then the answer is also a 2. The exponent does change, and what happens? Well, it appears to be that we take a 3, and then we add the 2 to get the 5. All right? So 3 plus 2 is 5, so we end up with the same base, a 2, and we raise it to the fifth power. All right? And that makes sense because of the way exponents work. Again, we're having 3 2's, we're having 2 2's, and now we have 5 2's raised, or 2 raised to itself 5 times. Okay? So the point that I'm trying to make here is when we're multiplying exponents, or terms with exponents, we can simply add the exponents themselves. So let's say instead of 2's, we have variables. Let's use a y. So, well, let's go to a different color here. Let's say we've got a y to the fifth power, and we want to multiply that by a y to the third power. Okay? Well, we could say that the answer to this is y to the 8th power. Okay? All we're doing is adding the exponents. 5 plus 3 is 8. It's y to the 8th power. And again, if you wanted me to draw this out, just think about what this means. Y to the fifth means 5 y's being multiplied by each other, right? And then we have, on top of that, we're multiplying it by 3 more y's. So we have a grand total of 8 y's being multiplied by each other. So it makes sense that that would be y to the 8th. All right. So it may seem a little bit odd at first that we're adding exponents when we're multiplying, but that's the way we do it. If we are multiplying variables or numbers with exponents, we can simply add the exponents to get our solution. All right. Now, one key point that needs to be made here is that these two bases have to be the same. So if I had, instead of 2 to the third times 2 to the second, if I had 2 to the third times maybe 4 to the second, all right, I can't do something weird like 2 times 4 is 8, add the exponents, and that's 5, so it's going to be 8 to the fifth. No, that doesn't work. We can't actually do this unless the bases are the same. So here we have a 2 as a base, here we have a 4 as a base. They're different, and because they're different, we can't just simply add their exponents. Again, think about what this means. It means a 2 times 2 times 2, and then we have our multiplication sign here, and then we have a 4 times a 4, okay? Which, if we were to multiply that out, is not 8 to the fifth or anything like that. It's very much different than that. It's actually, well, let's see, 4 times 4 is 16, times 2 is 32, times another 2 would be 64, times another 2 would be, what, 128? So that's 128. Definitely not 8 to the fifth. So you can see that one important thing you need to recognize is that the bases need to be the same in order for us to rewrite this with any kind of meaning when we talk about exponents. All right. So the reason we're talking about this is primarily for variables. So let's try a couple problems here. If I've got, let's see, x squared times y to the third times x to the fourth times y to the second, and maybe we'll just throw in another y to the third. Okay. And so I've got this product here that I'm looking for. I've got all these numbers that are being multiplied by each other. All right. So if they're being multiplied and we have exponents, then we're going to simply add the exponents for the common bases, the bases that are the same. So looking at this problem, we're going to say x squared. I can take that x squared and multiply it by this x to the fourth. Why? Because they have the same base. They don't have the same exponent, that's fine, but they do have to have the same base. All right, so multiplying an x squared times an x to the 4 is going to give me what? Hopefully you thought it would be x to the 6th. We add the exponents. Watch out, we don't multiply them. A lot of people make that mistake. We think, oh, we're multiplying here, so we must have to multiply the exponents. No, you add the exponents if you're multiplying. All right, so x squared times x to the fourth is x to the 6th. All right, then we can look at the rest of our variables here, and we can recognize that we've got, a bunch of y's. We got a y here, and a y here, right? So let's multiply those together. A y to the third times a y to the second is going to be y to the fifth, right? And y to the fifth times a y to the third is going to be a y to the 8th, right? Now the way to think of that is we're just saying this is going to be multiplied by a y to the third plus this 2 plus this 3, right? Because those are all of our y's. And that, of course, can be simplified to x to the 6th, y to the 8th. And that would be our solution. All right. Now, let's talk about another thing that we might run across here. What if we have something that looks like this. X times x squared times x times x. All right, and we're trying to multiply these together. All right. Well, when we're multiplying these, we want to add the exponents. They all have the same base, which is great. They all have the x, so we can add the exponents. Now, the question might become, well, what is the exponent for this x? I don't see anything up here. And like so many other things in math, if we don't see it, it is there, but it's an invisible 1. So an x by itself could also be written as x to the first power, meaning it's just being multiplied by itself once. It's just an x. All right, so x to the first. So all of these here could be considered x to the first, right? Now that we have an exponent in there, now it's a little bit easier to add these all up. So this is going to be equal to an x. The base is going to stay the same, but now we're going to add all these exponents. So we're going to add a 1 plus a 2 plus a 1 plus a 1, right? And that's going to give us x to the 5th, right? Okay, so pretty straightforward. It's not very complicated. The thing to remember is that when multiplying, and I stress multiplying, variables that have the same base, you can simply add the exponents. That is the moral of today's lesson, you might say. All right. Okay, let's try just one more, just for the fun of it here. And we'll back up here. We'll do another one down here just to see how you do. So let's think up one that's maybe a little more complicated. Maybe I'll just pull one out from the book here. So if I've got an m to the 3rd, let's see, pmx m squared x to the 3rd, p to the 5th. Okay, and if I were to tell you to simplify this, what would you do? Go ahead on a separate sheet of paper and see if you can actually simplify this. All right, so hopefully you came to a conclusion on what the solution would be on your paper, or I should say what the simplification would be on your paper. Let's go ahead and do it together. So we're going to start by just finding our common bases, okay? That's what we're looking for, bases that are the same. So here we have an m, here's an m, here's an m, and that's all of them. So we're going to end up with an m raised to the 3rd plus this one, which is the invisible 1, plus this one over here, which is a 2. So that's our m's, right? Now let's go ahead and go on, and we'll look at the next variable here is a p. And we have a p here. We also have a p here. So they're common bases. We'll multiply those together, and we multiply them together by adding the exponents. So 1 plus 5, right? Now all we have left is, excuse me. Oh, what color should we use? All we have left are the x's. So we have an x here and we have an x here. They're a common base. This x has an invisible 1 up there. So it's going to be an x to the 1st plus a 3, right? So finally, now all we have to do is just add all of this together. So m to the 3 plus 1 plus 2 is going to be 6. P to the 6 as well. And x to the 4. That would be our simplification for this expression. All right. Okay. Let's continue. Now we're going to talk about something a little bit different here. We're going to be talking about about adding like terms that have exponents. So we've already learned how to add like terms. If I have 3xy and I'm adding to that 5xy, we would recognize that these are like terms. The variables are the same. And so we would simply add the coefficients. 3 plus 5 is 8. So we get an 8xy. Now, just so that you don't get confused, just keep this organized in your mind. Notice that we're adding here, so we don't care about the exponents. All right, the exponents stayed the same. As a matter of fact, the variables stayed the same. We had an x and y in all of them, and the answer has an x and y in it. The only thing that changes when we're adding are the coefficients. Those are the things that change when we're adding. All right. In multiplication, it's not just the coefficients. As you'll see later, we didn't actually do any coefficients on any of these problems, but the variables do change in the sense that their powers change when we're multiplying. But when we're adding, the powers don't change on the variables, and the variables themselves don't change. All right, only the coefficients do. So just make sure you keep this straight. So what if we have variables that have exponents? What happens then? Well, the thing to remember is these do have exponents. They're just invisible. So this one has a 1, this one has a 1, this one has a 1, this one has a 1. You just don't see them. And think about what we did. In our answer, they also just have 1s. Like I said earlier, the exponents and the variables don't change at all. They stay the same. Only the variables do. So that really is pretty simple. So if we have something like 3z squared minus 5z squared minus 6z to the third. Okay, now let's simplify this. So we've got addition, subtraction. We just think of subtraction as addition. So we have addition going on within this expression. So we're going to look for like terms. And if we kind of go through our problem term by term, we'll say, okay, here's a term right here. Do we have any like terms with it? Now remember what that means. It means the variables have to be essentially exactly the same. So this has a z squared. Now this one also has a z squared, and that's all it has other than the coefficient -5. So these two are like terms. How about this third one? We have a z, but the variable, or the exponent is not the same. Here the exponent was a 2 for both of them. Here it's a 3. So is this a like term? The answer is no, it is not a like term. In order for it to be a like term, the variable and the exponent have to be the same. Just remember that. The variable and the exponent have to be the same in order for it to be a like term. So if we're adding these up, what do we get? Positive 3 and a -5 is a -2z squared. Notice that z squared is consistent all the way through. It doesn't change. And then we have this last term all by itself. It doesn't have any other like term with it, so it stays the same. This then would be our solution, our simplification for the problem. All right, so let's try a couple of these. A little bit more complicated maybe, only in the sense that they're bigger. So let's take a look at these. We're looking for like terms. We're trying to add these up. So x squared times y times p to the 5th. All right, let's start with that guy. What do we have? Do we have any like terms with him? And if you look through the problem, this one has an x, but it doesn't have the x squared, so that's not a like term. This one has an x, but again, oh, actually it is. In this case, it is squared, and this is squared, so that's good. It's got a y to the 1st, and it's got a p to the 5th. So these are, in fact, like terms. Okay. Finally, we have an x here, but again, it's not being squared, as this one is. So therefore, they're not like terms. This is to the 1st power, this is to the 2nd, so they would not be like terms. So taking these two terms, we can add those together. What do we get? Well, what's the coefficient for this term? Remember, in this case, it's invisible. It's a 1. There's an invisible 1 right here, right? What's the coefficient for this term? It's a positive 3. So a positive 3 and a positive 1 is going to be a 4. X squared, maybe we'll go p, well, actually, if we were to write it in alphabetical order, which you don't have to necessarily, but sometimes it's kind of nice to have a method to how you write these. So p to the 5th, x squared y would be the simplification for those two terms. Now, let's look for other like terms. We've got a 2xy squared p to the 5th. All right. Over here we have a y squared. Well, that matches. P to the 5th matches. X matches. So these are, in fact, like terms. So we can add them. Let's combine them. You have a positive 2 for a coefficient. You have a negative 7 for a coefficient. So they're going to combine to be a negative 5. And again, we'll just put it as p to the 5th xy squared. Okay? That is our simplification right there. There's nothing more that we can do in that problem. They are not like terms, so we can't combine them. All right? Let's try another one. So if I've got 2x squared, we're looking for like terms here. 2x squared, do we see any others that are like to that? Well, this has an x squared, which is great, but it also has a y. This one doesn't, so that's not a like term. This one, for the same reason, has an x squared, but it has a y squared. This one has an x squared, but it has a y. This one has an x squared and a y squared, so nothing matches with this 2x squared. So he's all by himself. So he's just going to stay 2x squared. All right. Now let's look for a common, a like term with this one. So we have a positive 3yx squared. Do we see any? Well, yeah, here's a yx squared, which would be similar or the same. So this guy is a like term. And then this one's y squared, x squared. It is not. So now we can combine these two for a positive 2x squared y, right? And then finally, we've got this positive x squared y squared. Notice x squared, y squared are also present over here. That would be a like term. We can combine them. This is a positive 1. So a positive 1 and a negative 4 is going to give us a negative 3 x squared, y squared. Excellent. That would be our solution. All right. Let's move on. We're going to try just a couple more before we stop here. So go ahead and try this on a separate sheet of paper by yourself. And then we'll do it together. All right, so 2x squared y to the third. Do we have a common, or not a common, excuse me, do we have a like term with this? X squared y to the third? Well, sure we do, right here, right? So we can combine those. A negative 8 and a positive 2 is going to be a negative 6 x squared y to the third. All right, then what about these? We have a positive xy. This is also a yx, but they have the same variables. And actually, I don't want to cover up that minus sign there. There we go. So we have a positive xy and negative 5xy. That's, again, positive 1. So we end up with, when we combine those, a negative 4xy, and that would be our solution. All right. Go ahead and try this one on a separate sheet, and we'll do it together. All right, so we've got x to the 6th y. This would be a common term, or excuse me, a like term. And do we have anything else? We're looking for an x to the 6th and a y. This is close, but that's kind of reversed. This is an x to the 1, y to the 6th instead of x to the 6, y to the 1. So that's not a like term. So we're done. We're just those two. So if we add those two, we have a positive 1 right here, another positive 1 right here. So we end up with 2 x to the 6th y. Now here we have an xy. Oop. Change color here. Here we have a positive xy. Do we have anything that is a like term with that? Well, the only thing we have left is over here, and this actually does not. This is an xy to the 6th. So this one's going to be all by itself. And then finally, of course, the last one is also going to be all by itself because there's nothing that can go with that. And that would be our solution. All right. So just as a real quick recap here, remember what we learned today. If you are multiplying variables with exponents and the bases are the same, you can simply add the exponents to get your solution. All right. And then as far as like terms go, if you have two terms that are like terms and they have exponents, and the exponents are the same, then you add the coefficients to get your solution. So this one deals with multiplication. This one deals with addition. All right. In addition, you're adding the coefficients. In multiplication, you're adding the exponents. All right. So that's kind of just a real quick summary of this lesson. So go ahead and start working on your homework problems. And if you have any questions, you know where to ask them in OneNote. And we'll continue tomorrow.